Welcome back to our exploration of the mysteries of cosmology. In the previous lecture, I demonstrated that the data on Type 1a supernovae fairly convincingly demonstrate that right now the energy content of the universe is dominated by a repulsive form of dark energy, something pushing space faster and faster away from itself, stretching it effectively. There is now other data suggesting that this conclusion is correct, and the most convincing data come from the cosmic microwave background radiation. The argument that I'll describe in this lecture is somewhat involved, but I'd like to show it to you because it's so beautiful, it's so compelling. Together with the Type 1a supernovae, the two techniques give such a complete picture of at least what the composition of the cosmos is that I want to describe it in some detail. But you can feel free to just listen to and absorb only the simplest parts, if that's what you'd like. This lecture and the next couple of lectures will give you all of the gory details that will allow you to come to a more complete understanding of what's going on. But even the more light material, I think, should be fun to absorb. Well, let me go back to a map that I showed you earlier of the Earth. This is the projection of a sphere onto a two-dimensional sheet of paper where one preserves the areas of continents. It's called a Mulvida projection. And we can make a map of the Earth in this way that shows the surface temperature, the average temperature, for example, in June of 1992, where the deep blue colors indicate very cold temperatures down to minus 63 degrees Celsius, and the orange represents hot temperatures all the way up to 37 degrees Celsius. And you see that over the course of June 1992, the average temperatures were generally low at the poles and generally high in the equatorial regions. And there are pockets where the temperature is low, like in the Himalayan range right here. All right? So one can make a map of the temperature of the Earth in this way, the distribution of temperatures over the surface of the Earth. In a similar way, we can make a map of the temperature of space from the cosmic microwave background radiation. It effectively tells us what the temperature of different parts of space is. And in this projection here, you can see that, in fact, the temperature is not perfectly uniform. It's somewhat hotter in one region and somewhat cooler in another. And sort of in between, there's an average temperature midway between those two. Now, this is easily understood as being an effect of the motion of our Milky Way galaxy through the framework of the universe. We've got this expanding universe like an expanding balloon, and most galaxies are just flowing away from each other due to the uniform stretching of space. But galaxies also pull on one another due to gravity. So they move through space in addition to being pulled along with the stretching of space. It's as though the raisins in my expanding loaf of raisin bread had springs between them and sort of pulled on each other, moving them through the dough. So our motion, the Milky Way's motion through the universe, causes the microwave background radiation to be somewhat more intense, somewhat hotter in one direction, the direction of our motion, due to the gravitational pull of other galaxies. And it tends to be cooler in the opposite direction, since we're moving away from that radiation and it's Doppler redshifted. Okay? Once we remove the Milky Way's motion through the universe, the resulting map of the sky is incredibly uniform. Look at that. Nothing of interest, nothing changing in this map. The whole universe has a temperature of about 3 degrees above absolute zero. More precisely, 2.725 plus or minus 0.002 degrees. That is the temperature of intergalactic space. That is the temperature of the universe. It's not the temperature here on Earth. We wouldn't survive too well in such a deep freeze. We're heated, of course, by the sun. But the average temperature of the universe as a whole is merely 3 degrees. And this is the afterglow of the Big Bang. Well, we actually expect the temperature to show some inhomogeneities. And that's because giant clusters of galaxies like this one exist in the universe. We see them all over the place. We're part of a small group of galaxies, the local group. There's the Virgo cluster of galaxies 60 million light years away. We and Virgo and a bunch of other clusters form a supercluster. There are other superclusters, and there are voids and things. There's structure in the universe. Right now, the universe has structure within it. That structure had to have grown through the gravitational accumulation and contraction of certain regions of space at the expense of others, which grew large voids, relatively empty regions. Such gravitational growth had to have started from seeds, small density inhomogeneities, which gradually grew in size, the density contrast between the clumps and the voids gradually increasing with time. Well, the denser clumps in the universe would have hindered the exit of photons from those regions. Photons would lose energy on their way out from dense regions, and they wouldn't lose as much energy on their way out from voids. So in fact, we expect that the density inhomogeneities would have had some imprint in the observed temperature of the microwave background radiation because of this gravitational redshifting of light from the denser regions and less redshifting from the less dense regions. And there are other effects as well. But in any case, we expect there to be minuscule variations in the temperature of the microwave background radiation. Here is the growth of structure in the universe from these small variations that existed at the time that matter became neutral, when the universe was around 380,000 years old and a temperature of 3,000 degrees Kelvin. Those then clumped more and more through time, eventually forming the first stars and quasars, gradually clumping more and more, and finally forming the galaxies and the clusters of galaxies of today. But the clumps had to have existed back when the universe was only 380,000 years old. In fact, they had to have existed even before that. The clumps, when the universe was 380,000 years old, which grew to form galaxies and clusters of galaxies, had to have been present and had to have formed in an even earlier stage of the universe's existence, when it was only a tiny of a fraction of a second old, just past the dawn of time. At that time, a process known as inflation, an extremely rapid, indeed an exponential growth of the universe, blew it up to an immense size. I'll discuss that in one of the final lectures. But those small ripples in the fabric of space-time had to have been created during that first split second of the universe's existence. And they have to have been stretched themselves in order to form clumps that were big enough at the time of 380,000 years to have then led to the subsequent formation of large-scale structure in the universe. So the clumps must have existed essentially from day one. Indeed, from microsecond one. And we should find some imprint of them in the microwave background. To look back in time at, again, the origin of these imprints, we look from the perspective of a spacecraft, seeing the microwave background from far, far away. How far? Through our solar system, through interstellar space, through all the multitudes of stars and gas clouds in our galaxy, beyond even our galaxy, way beyond our galaxy, on the way to other galaxies. This is the space through which that light from the microwave background traveled. Back, back, back we go to the clusters and the voids between them. And finally, to the quasars and the first stars. And before that, the clumps from which they formed. And before that, to a time when the universe was quite hot and only starting to become neutral, a time of 380,000 years after the Big Bang. And still before that, those clumps must have existed, bam, a split second after the time of creation. Well, it's amazing that we can even look for imprints in space, in the structure of space, whose origin is that far back in time. It's amazing that we can even attempt to achieve that. The COBE satellite in the early 1990s was the first to actually see these imprints. It precisely measured the temperature of the microwave background, 2.725 degrees. But more importantly, it saw variations in the temperature. Slightly hotter regions are red, slightly cooler ones are blue in this map of the sky. This was an amazing achievement for COBE because this measurement had eluded astronomers for over a decade. We were searching for these tiny imprints in the structure of space, visible from way back when. Well, since COBE's launch in 1990 and its detection of the imprints in 1992, there's been a lot of progress made with other kinds of microwave background experiments. In particular, people have sent microwave telescopes up in gondolas high into the Earth's atmosphere, especially from cold, dry regions such as the Antarctic, shown here. In the Antarctic, it's so cold that the water has mostly frozen out of the atmosphere. And so the atmosphere is very, very dry, and this allows better measurement of the feeble microwaves coming through. Boomerang was one of these instruments. It was launched into the atmosphere, it flew around for about 10 days, and it came back to about the same place from which it was launched, hence the name Boomerang. And there were other experiments as well, from Canada, from the high plains of Bolivia, and elsewhere. They found stunning variations in the microwave background on a much smaller angular scale than those found by COBE. In this map, you can see tiny hot spots, the red regions, and tiny cold spots, or cooler spots, the blue regions. And when I say hot and cold, or hotter and cooler, I mean variations of a millionth of a degree. That's what they're measuring here. A few millionths of a degree hotter and a few millionths of a degree cooler. The uniformity of the microwave background is stunning. It's much, much smoother than a baby's bottom. Okay? These are tiny little variations, but they saw them. And they saw them on angular scales much smaller than those seen by COBE. The smallest structures that COBE could see were about 10 degrees in size, maybe 2/3 of the angular size of an outstretched hand. Boomerang and Maxima and other instruments measured variations on subangular scales, sub 1 degree scales. Well, you can see here that there's sort of a preferred size for these fluctuations. There's many little dots that are about the same size, and there are some bigger ones and there are some smaller ones, but many of them have about the same size. We expect, in fact, fluctuations in the early universe to have had certain preferred scales over which the density was higher or lower. Basically, there were sound waves, or the analog of sound waves in the early universe. Certain regions were trying to get compressed because gravity was pulling them in, but radiation pressure, photons, was pushing those regions out. And there was sort of a give and take between gravity pulling in and radiation pushing out. This set up the analog of sound waves, pressure waves through the universe. And because of details of how the universe behaved, certain waves grew, others were diminished in size. And the overall distribution of wavelengths then results in something that has a preferred size, as you can see here. Now we can calculate in physical scale how big those fluctuations should have been. And that will translate to a preferred angular scale. But first we need to consider the geometry of the universe and what relationship there is between a physical scale and an observed angular scale. Suppose you've got an alien slug here who is firing 2 parallel laser beams. In a flat universe, one with 0 curvature, those laser beams are parallel. They maintain the same separation from one another throughout time. In a positively curved universe, a closed one like this, the rays separate but then eventually come together again and hit you in the back. This is like a balloon. And in a negatively curved hyperbolic universe, the rays separate from each other more quickly and never come back. Well, this means that a given physical size translates into a different angular size when seen from a great distance. In a flat universe, a meter stick looks kind of like this, and it subtends an angle that's some angle, all right? But in a positively curved universe, the light rays travel along these curved paths, and the same meter stick subtends a much bigger angle. In a negatively curved universe, the light rays tend to converge like so, and the same meter stick subtends a smaller angle. So what we have then is that a given physical size subtends a different angular size depending on the geometry of the universe. So we can look at these fluctuations and we can observe how big they appear to be and translate that into a true geometry of the universe. Here are the various fluctuations. We will look at them with a microwave satellite, and we will see that in flat space they have a certain preferred angular size. In a positively curved space they look bigger, and in a negatively curved space they look smaller, like that. So, in flat space, a given physical size is of intermediate angular size between that in negatively curved space and positively curved space. Well, the boomerang map shows these fluctuations, and in fact, their size, their angular size, corresponds with what is expected in a flat universe, not in a positively curved or a negatively curved universe, a flat universe. That means, according to the general theory of relativity, that the total matter-energy content of the universe must be unity. Omega total, must be unity, because that, in general relativity, is what produces flat space. Well, gosh, we have already seen that clusters of galaxies and galaxies spread throughout the universe, when all added together, give an omega of matter, of gravitating matter, that's only about 0.3. In fact, from the supernova studies, we get 0.28. But the total omega must be 1. So about 0.7 of it must be something other than gravitating matter. It can't be in clusters of galaxies, because the census of matter in clusters of galaxies has already been taken. And omega of the matter in clusters is only 0.3. Could it be some sort of hot material that's spread uniformly throughout the universe? We don't think so, because it would mess up the formation of large-scale structure in the universe. Here's a map of what the universe looks like. It's actually a computer-generated diagram. There are filaments and voids and superclusters and clusters and things. These all formed as a result of gravitational accumulation of matter. And we can see that they exist in the universe because here's a map plotting redshift, or look-back time, or distance. All those are equivalent in one way or another, versus position in the sky. And you can see great clusters and voids and superclusters. There's a bubble-like, filamentary structure of material in the universe. And to grow that structure, you need to have gravitating matter in clusters, but very little or no gravitating matter spread uniformly through the universe. If such matter existed, it would mess up the formation of large-scale structure. Here in this simulation, you can see the growth of perturbations over time. And they are gradually accumulating into denser and denser clumps and emptier voids. And this would not occur properly if there were a bunch of gravitating but uniformly spread out material in the universe. It would mess up the formation of large-scale structure. Here's a simulation of a cluster of galaxies forming. You can see all the galaxies coming together, whizzing around, gravitationally attracting and eventually merging with one another. This would be messed up if there were a bunch of so-called hot dark matter. material that is gravitating but is hot and hence uniformly spread out through the universe, not clumping in the clusters of galaxies. The presence of such a material would hinder the formation of such structures. And since we see them, we can say with considerable confidence that the matter content of the universe is largely, if not entirely, what is in the clusters and in the superclusters. So omega matter is around 0.3, and the remaining omega x something is 0.7, because 0.3 and 0.7 add up to 1 the last time I checked on my calculator. All right, so there's something that's out there. And we knew this as early as 2001 or 2002 from the existing microwave background measurements. But recently, the microwave anisotropy probe has shown us that this stuff really does exist beyond any shadow of a doubt. Here's an artist's rendition of the microwave anisotropy probe. It's named after David Wilkinson, one of the Princeton physicists who first understood the nature of the cosmic microwave background radiation that Penzias and Wilson discovered, and who was a prominent member of the team that was building this satellite. He died not long ago, but not before he found out the results of the experiment. Here is their map of the universe. It's beautifully detailed. Look at all these tiny little freckles in the temperature of the microwave background. They're measured with exquisite clarity with the Wilkinson microwave anisotropy probe. And here I show the same projection but on a sphere that's rotating. This may be more familiar to you. This is the sphere of the sky, the celestial sphere, on which these little freckles are superposed. The improvement from COBE to WMAP was amazing. There's the COBE map, and we will now go to the WMAP. Wow, look at that improvement in clarity. It's like you've got terrible vision, 2400 vision, and now you put on this wonderful set of glasses or contact lenses that lets you see the universe clearly. It's a beautiful measurement, and here the details of the microwave background can be seen, and an analysis can be made of the sizes of these various clumps, and the size of the clumps can be plotted on the horizontal axis as a function of how many such clumps there are along the vertical axis. And you can see that there's a preponderance of clumps that have a size of around 1 degree in the sky. There's a preponderance of clumps that are about twice the size of the full moon. This translates quite clearly into an omega of unity, a flat geometry, because a size, an angular size for the clumps of 1 degree corresponds to the physical size that we know these structures to have had early in the universe, because we can calculate them. This correspondence holds only if the light rays followed Euclidean flat trajectories. That is, not curves bulging outwards like this, not curves coming inwards like that, but Euclidean straight lines. That's the only conclusion that can be drawn. So WMAP shows us with greater precision what we thought we already knew based on the earlier measurements, that our universe is flat. Now that doesn't mean it's necessarily infinite. It could be that omega is slightly bigger than unity, 1.01 or something like that. In that case, the universe is still a beach ball, a closed balloon. But it would be really, really big. It's so big that out to the distance to which we can see, we can't notice any deviation from flatness. We can't notice this curvature. It's kind of like living in the plains states and looking out. It's easy to come to the conclusion that the Earth is flat. That's not an unreasonable conclusion. You can't see far enough to easily detect the curvature of the Earth because your range of vision is so much smaller than the size of the Earth. So too, our range of vision might simply be too small to detect the curvature of the universe. So here's a sign that I saw in California driving along the highway. There's a little place that sells fruit, Casa de Fruta. You can go 24,886 miles in the same direction in which you're driving right now, or you can turn around and go 15 miles behind you to get fruit from this little fruit stand. If you go far enough in a positively curved universe, you'll come back to the place from which you started, or you can head backwards, and it's a much shorter distance. Well, in our case, the universe might be a Google miles in diameter, a Google being 10 to the 100th power. It's one of my favorite numbers. An even better number is a Googleplex, 10 to the Google power, 10 to the 10 to the 100. And indeed, this may sound crazy, but as I'll show you in the last few lectures, we now have theoretical reasons to believe that the universe may be truly immense, much, much bigger than the distances to which we can see, much, much bigger than the distance to the cosmic microwave background radiation. So big that, in fact, it's like we're an ant, or even smaller, living on the surface of the Earth. Well, the WMAP results and the previous microwave background results showed pretty clearly that our supernova results were correct. The matter density in the universe appears to be around 0.27 or 0.28. The rest is some sort of a dark repulsive energy. Not a gravitating, uniformly spread out form of matter, but some sort of new stuff. And this was immensely gratifying to both teams, because a lot of people, quite correctly, didn't take us very seriously initially, because our conclusion was so outrageous sounding. Dark repulsive energy, that's weird. No one really expected that. But now an independent set of measurements suggests the same thing. So the composition of the universe is as follows. 27% or 28%, something like that, consists of matter. 73% consists of dark energy. All right? More than 2/3, indeed nearly 3/4 of the matter energy content of the universe is this dark repulsive stuff. That's weird. We don't know what that stuff is. I'll discuss possibilities in the next few lectures. But whatever it is, it's really weird. What about the remaining quarter of the universe, the 27 or 28% that's matter in this diagram? What do we know about matter? Painfully little, it turns out. Painfully little. It turns out that the visible content of the universe, the visible stars and gas, are only a small fraction of this entire matter content of 27 or 28% that we showed in that pie chart. What we can see is only a small fraction of that. Now, good evidence for this comes from studying the so-called rotation curves of spiral galaxies such as this one. If you measure the speed with which a galaxy is rotating as a function of distance from the center, you find that the outermost parts are rotating just about as fast as parts closer in. In the late 1970s, Vera Rubin, among others, showed this quite forcefully, that the outer parts of galaxies, way out where there are very few stars to be seen, are rotating about as rapidly as more inner parts where there are lots of stars. Now, when you go through the math and the physics of this, the implication is that there's a whole lot of matter enclosed within the orbits of the outermost stars. Far more matter than can be accounted for using just the visible stars and gas. There's a lot of stuff out there. And the farther out you go in a galaxy, the more dominated it appears to be by dark, invisible, sometimes called missing matter. I don't like to call it missing mass or missing matter because it's not missing, it's there. We can deduce that it's there from the gravitational motions of stars. But we can't see it. And Vera Rubin understood this. Decades earlier, Fritz Zwicky studied clusters of galaxies. He studied the motions of galaxies such as in this cluster. And he found that they're moving around so quickly that to remain bound within clusters, there has to be much, much more matter than what can be seen in terms of visible stars and gas. Indeed, clusters of galaxies are completely dominated by dark matter. And Fritz Zwicky, shown here, knew this in 1933. 70 years ago, he proposed the existence of dark matter. An idea so far ahead of its time that it truly wasn't taken seriously until decades later, really until Vera Rubin started measuring the rotation curves of galaxies. But Zwicky suggested it 70 years ago. Now, one reason perhaps he wasn't taken very seriously is that he was a rather arrogant and abrasive fellow. You can see in this photograph, he doesn't look like he's a particularly nice guy, at least not right at this moment. He ridiculed his colleagues at the California Institute of Technology, Caltech, in Pasadena, California. He referred to them as spherical bastards because they're bastards any way you look at them. Well, you know, if someone refers to you as a spherical bastard, you're not going to be inclined to take them very seriously. And so, indeed, Zwicky was largely ignored. He was viewed as sort of a crazy guy. But in fact, he had so many great ideas, including the idea that a massive star explodes as a result of the collapse of its core and then a bounce outward of its outer atmosphere. That was his idea as well, and it turned out to be correct. He had a lot of correct ideas. So there's a lot of dark matter in the universe. The visible matter is essentially negligible. It's only 1/2 to 1% of the total mass energy content of the universe. So of this 27 or 28%, only 1/2 to 1% is the visible stuff. The remainder is dark matter. It dominates. Well, what could it be? What could be this stuff? In 1998, during my course for the teaching company, I gave you a number of possible candidates for dark matter. I said that they could be black holes, neutron stars, white dwarfs, brown dwarfs, or massive lone planets, Jupiters I called them. These 5 categories are what are called massive compact halo objects, MACHOs. In the galaxies, one could figure out that most of this dark matter resides not in the disk of a galaxy, not in the plane of a galaxy, but in a roughly spherical halo. And it was postulated that the stuff in this halo might be these MACHOs, smallish things that are nevertheless massive. Other possibilities were neutrinos, hot gas, various exotic subatomic particles, and things that I call golf balls. Basically, ball or rock-sized objects which formed for some reason unknown early in the universe and fills the halo of our galaxy and other galaxies, but is very difficult to detect. I mean, if you don't have a light bulb shining on a golf ball, how are you going to see it? It doesn't lens things very well, and it doesn't reflect much. And so, you know, though we have no origin for such objects, it's still a theoretical possibility that they constitute the dark matter. Well, in the last few years, a lot of progress has been made in effectively ruling out MACHOs as the dominant dark matter constituent. And I described in 1998 an experiment that sought to measure or sought to detect MACHOs toward the direction of 2 satellite galaxies outside our Milky Way, the Large and Small Magellanic Clouds. If there are MACHOs in the halo of our galaxy, occasionally they will pass along our line of sight to stars in either one of those 2 galaxies, and they will gravitationally lens the light from those stars. So here I illustrate what I'm saying. The Earth is at the left, the Large Magellanic Cloud is at the right. A MACHO that's moving through our halo for a moment might be exactly collinear with the Earth and this star. If it's in such a configuration, it bends the light from the star and focuses it towards us. So the star, for a brief time, can look considerably brighter than it normally does. Here is a light curve. Intensity or brightness versus time of such a lens star. It's constant before the lensing event. It increases during the lensing event, and then it decreases afterwards and remains constant. And the rise in brightness is the same at red wavelengths as at blue wavelengths, because the lensing is a property of space-time and doesn't care about the wavelength of light which is being lensed. So this is a distinctive signature of gravitational lensing. And in 1998, I said that a number of such lensing events had been discovered by the Macho team and had been provisionally attributed to machos in the halo of our galaxy. So I thought in 1998 that we were making big progress in this area, that we had identified a fair amount of the dark matter in our halo, and presumably then in the halos of other galaxies. Well, since then, we've gone a little bit backwards in a sense. Here's a Large Magellanic Cloud, and it turns out that in 2 or 3 of the cases where we can determine the distance of the macho, of the lensing object, I can't go into the details right now, but in a few cases we can determine where they are. They are apparently low-mass stars in the Large Magellanic Cloud itself. They are not in the halo of our galaxy. So if 2 out of 2, or 3 of the 3 objects with measured distances all turn out to be in the Magellanic Cloud and not in our halo, the suggestion is that many, if not most, of the so-called machos that had been detected are really stars in the Magellanic Cloud and are not part of our halo at all. So in fact, now we think that at most 20% of the halo of our galaxy consists of these machos. They basically don't exist, or there are very few of them. So, if black holes and neutron stars and white dwarfs and Jupiters and things like that are ruled out because they would cause a lensing effect, what's left? Let's go back to our list. How about neutrinos? We've shown that they have a non-zero mass, but the upper limit to what their mass is, we know it's between 0 and some limit, though we don't know precisely what it is. The upper limit translates into a total energy content of the neutrinos, which is basically negligible in the universe. 0.3% of the mass energy density of the universe might be neutrinos. Could it be hot gas? Quite possibly. I'll discuss that in a few minutes. Could it be exotic subatomic particles left over from the Big Bang? Could be. We don't know what the Big Bang produced. Could it be these golf balls? Well, possibly, but again, we really don't know how they would have formed. There's huge obstacles to the formation of rocks and golf balls in the halos of galaxies, whereas there's no obstacle in principle to forming exotic subatomic particles or hot gas. Now, in the past few years, tremendous progress has been made. Indeed, we've found that hot gas does make up 3 to 4% of the mass energy density of the universe. And the way that's been found is by looking at clusters of galaxies with X-ray telescopes. Here I show a cluster glowing profusely at X-ray wavelengths and imaged with the Chandra X-ray Observatory. This cluster has gas with a temperature of 10 to 100 million degrees. It glows at X-ray wavelengths, not at optical wavelengths. So of course we didn't see it before. But now we have good X-ray telescopes and we can see this glowing gas. Moreover, smaller, looser groups of galaxies, such as this one, also have gas, but it glows not quite at such a high temperature, but rather a temperature of only about 1 million degrees. Warm gas, not super hot. Such gas glows only in a feeble way at X-ray wavelengths. And so until there were really good X-ray telescopes, we simply didn't know that that gas was there. We can also detect the presence of that gas by the absorption lines that it produces in the spectra of background quasars. Those measurements have been made, and people have detected the signature of 1 million degree gas in loosely bound groups like this. So when you put it all together, 3 or 4% of the mass energy density of the universe may be this hot gas. 0.5 to 1% is the visible stuff of the universe. That all adds up to a total of something like 3.5 to 5% of the material in the universe being normal kinds of matter. Visible stars, visible gas, hot gas made out of protons and neutrons and normal kind of matter. Something like 3.5 to 5%. That's all. Not 27%. And in fact, now we think that the number is precisely 4.4% for the normal matter content of the universe. And we know this from two arguments. First, deuterium was produced profusely in the early history of the universe when it was just a couple of minutes old. Protons and neutrons combined to form deuterons and photons. That happened when the universe was less than 100 seconds old, or about 100 seconds old. But just as soon as the deuterons were made, they got destroyed. Deuterium can combine with deuterium to form helium-3. Okay? It can also combine with this helium-3 to form helium-4, and so on. So deuterium rapidly gets destroyed in the universe if the universe's density remains high for a pretty long time. The fact that deuterium is present in today's universe at a reasonably high level, it's 3 parts per 100,000 compared with hydrogen, which doesn't sound very high, but considering how rapidly, how easily deuterium is destroyed early in the history of the universe, the fact that 3 atoms of deuterium for every 100,000 atoms of hydrogen remain indicates that the matter density of the early universe could not have remained high for very long, and that translates into a total matter density today of only 4.4%. Moreover, WMAP independently showed that 4.4% of the matter energy density of the universe is this normal stuff consisting of protons and neutrons. So now let's take a look at a census of the universe. The normal stuff is 4.4 or 4.5%. That's the free hydrogen and helium that we see in the glowing hot gas of clusters of galaxies and small groups of galaxies. The stars and visible gas are something like 0.5%. The total of these two categories is 4.4 or 4.5%, something like that. And that's from the deuterium measurements and from the completely independent WMAP measurements. So this quantity is known quite well. The neutrino quantity isn't known quite so well, but it's pretty well known to be something like, 0.3% or less. So that's the ghostly neutrinos. Heavy elements in the universe are very small, 0.03%. So all this adds up to only about 5%. All of the known material in the universe is only 5% of what is out there. That means that 95% of the universe is unknown to us. Looking back at this pie chart, the dark energy is 73%. The dark matter is 22%, and that doesn't include the dark matter that's in the halos and clusters of galaxies that glows at X-ray wavelengths. It's not normal neutrons and protons and normal matter that have already been properly taken into account in the deuterium calculations and in the WMAP measurements. Probably it's some sort of exotic subatomic particle. There may be all sorts of particles of a still unknown nature that are produced shortly after the Big Bang and which have escaped detection in any of our normal ways of detecting particles. That's the best bet right now for what the majority of the dark matter really is. But I should emphasize that we really don't know. We don't know what the 22% that's dark matter is. And even more troubling, we really don't know what the dark energy is, what 73% of the universe is. So it's disconcerting that 95% of the universe is of a form of matter or energy of which we have no direct understanding and no direct experimental measurements. I'm glad that we know now what the remaining 5% is, but it's disconcerting, to say the least, that we are ignorant of 95% of the mass and energy in the universe.